All right, hopefully we should be recording now. We will get started. Um, Thank you guys all for coming to this little kickoff meeting we've planned. We're hoping to have this be a resource. So just so you know, our agenda will be to go over some event logistics, tips and tricks, but then also just some intro to structural engineering as well. So this would be a great video to show students and have them watch as well. So with that, we will do a quick little introduction of our three speakers today. Hopefully it'll change slides. Here we go. So first off, I'm Cameron Fraley. I am the chair for the Young Members Group for the Structural Engineers Association, which I'll talk a little bit more about in a second, but we are the organization that puts on this event every year. I'm also an structural engineer with Kaufman Engineers here in the Denver area. And I went to Washington State University, where I obtained my master's in civil engineering. And I have been an engineer with Kaufman for 4 years. Joe?
Yeah, I'm Joe Elliston. I am a new part of the SEAC YMG helping put on this event this year. I am not a licensed PE. I'm still just an EI. I work at Benish as a structural designer in railroad structures. And I went to UNO for my bachelor's and master's then in structural engineering. And I've been with Benish for a little over a year now.
Cool. And I'm Thomas Tarsha. I work for Simpson Strong Tie. I actually graduated from Colorado School of Mines, got my bachelor's and my master's there. And yeah, I've been practicing structural engineering for the last 5 or so years.
Perfect. Thanks, guys. So like I mentioned, I wanted to talk a little bit more about the SEAC YMG. So SEAC is the Structural Engineers Association of Colorado. So we're a group where structural engineers can get together and work to better our field. So the main goals of the young members group is to get young engineers involved in the organization through professional events where they can network, happy hours where they can meet each other, and educational activities. So we've done, workshops and presentations, um, and we also work to get students involved. So that's why we have this event for all age students, but we also encourage university age students to come to our events. So I am the committee chair. I've been so the last couple of years. If you have any other questions about SEAC or the YMG, that email that I email most folks with about the competition is the best way to reach me. I also wanted to go into a little bit of history about the competition. This actually has been going on since 2006, but originally the event was a holiday party for a local engineering group called Ascent up in Boulder. And in 2008, they decided to include other professional engineering and architecture firms. That way they could compete against each other and make it a bit more of a competition. And then students started competing in 2009. So the event has been around for a while. It's just been growing a lot in recent years. Um, Portland has also been doing a competition similar to Denver. But overall, yeah, we've had, I think this number is probably a lot higher now. I haven't updated it, but over 65 professional teams and over 50 student teams. Last year alone, we had over 20 student teams register. So I would have to say that that number is quite a bit higher now. But yeah, we're trying to keep growing this and get people interested in structural engineering as a field. Um, so just a little bit quick about the competition. I think most folks on here are familiar, but I'll talk briefly about it. The competition is for gingerbread bridges. So the point is to build an edible gingerbread bridge that spans about 2 feet, 24 to 30 inches is the recommended lengths. And then we load test them. So there's some photos here at the bottom where you can see some of the bridges being load tested. And the winners, there's 3 different categories. There's a winner for the best structural design. So that's the bridge that can hold the most load compared to its self weight. And then there's an architectural design. So we'll have a panel of actual architects in the Denver area come and judge the bridges for architecture. And then we'll also have people's choice where everyone in attendance can vote on their favorite bridge. So super fun competition in a way to get an introduction into structural engineering. So then a couple logistics I wanted to cover really quick. The venue this year is the same as last year. It's in Friedhof Hall, which is in the Green Center at the Colorado School of Mines. It is going to be on November 15th. That other important date I put on there is that registration does close at the end of this week on the 19th. So if you haven't registered, please make sure to do so on the website. You can email me with any of those questions. Food and drinks will be similar to the past. We'll have some light snacks available, some coffees and teas, but if you please plan to have your students bring stack lunches or plan to purchase one from the dining options on campus. Expenses, we are hoping to have up to $75 per team for reimbursement for materials. So make sure to keep your receipts and submit those. If you have questions about this sort of thing, we can go over it at the end. And then schedule event will be starting at 9 a.m. Judging, you have 30 minutes to set up. We'll have judging begin around 9:30 or so, and then testing around 10 or 10:15. Last year, the event concluded around noon. We'll be shooting for a similar time frame, but it could go a little bit longer depending on testing. So just be prepared for that. Okay, so I think that
This is the
is the
start of my
end
portion.
of my slides. So yeah, Joe, take it away, and we'll talk a little bit more about the competition at the end.
So this portion is going to be especially for our high school and younger teams that are going to be taking part in the Gingerbread Bridge building competition this year. My hopeful takeaways, I'm going to be talking about what civil engineering, what structural engineering really are. So hopefully your kids are going to be able to learn about what our wonderful field is, gain a broader understanding of the vast options of the field of civil engineering, because it does cover a lot of different types of work. And inspire them to find the field that they're passionate about, even if it's not civil engineering. So, what is civil engineering? It is the design, construction, and maintenance of physical and naturally built infrastructure, as well as the environment. It is also known as one of the oldest professions and oldest types of engineering in the history of mankind, because we've always needed infrastructure. Ever since we've had places to live and things to move from one end of the world to the other, and a need for clean water, we've had civil engineering. So we design roadways, we design bridges, buildings, wastewater systems. It's the reason we have clean water to drink nowadays, and transportation hubs, like many of our Denver natives will know, Union Station. That is a beautiful piece of civil engineering. So civil engineering, as I said, is a very, very broad field, and it is broken down into a handful of subdisciplines that you can specialize into with the work that you do after you graduate. So number one, hydraulics and hydrology. This is going to be stormwaters, sewers, dams, retention ponds. These are the things that prevent flooding in cities and make sure that we are able to collect water, clean it, and provide it to the rest of the city to drink and shower, and make sure that we don't have our houses underwater. Construction engineering, that is going to be scaffolding design. You will manage contractors or do construction inspection. That's making sure that everything that we design in an office gets put into the ground within spec and is actually what we intended. And we have geotech and materials. They do soil analysis, materials testing and design. They're the reasons that we have buildings and bridges that don't sink into the ground or have massive slope failures on the walls in the when you're driving up in the mountains. You'll see those protective nets. That's because geotechnical engineers provide us where we have risk of failure and collapse. Roadway and transportation, they design road curvature, interchange design, traffic analysis, helping us maintain the flow of people throughout cities. They're the reason that we don't have as bad a rush hour here as some other cities, though we all do love to complain about traffic design because they are the reason that we still have to commute. And then there's environmental. They do wetlands protections, ecological studies. They do pollutant runoff. They'll work with landfills to make sure that the things that get put there aren't running into our soil and contaminating our groundwater. And then we have me, Cameron, and Thomas, structural engineering. We design bridges, buildings, and walls. And today our main focus is going to be on bridges for the Gingerbread Bridge building competition. So kind of a little checklist to know, is this a field that your kids might be interested in? Or if you're in high school and you're trying to think about what major you want to pick. This is a good checklist of what a lot of your cohorts in civil engineering are going to be like. Enjoying math and physics. Civil engineering is all about the application of simple physics and kinematics and lots of math. It applies a broad and diverse mindset to tackle problems. No civil engineering design challenge is going to be the same as any other. Every building, bridge, wall, site plan is going to be different. And that is super fun because that means your work hopefully won't get too stagnant. I know for myself, I get to work on a lot of weird, different design challenges from every project. And it's all about determining good creative solutions that are effective and economical and fast. That way we keep bridges standing. Nobody wants a bridge collapsing, and everybody wants quick, easy repairs that minimize the impact to traffic and the people around the structure that you're working on. Teamwork. As I said, it's a diverse field. We work with everybody in lots of these different disciplines. So you're collaborating with lots of people with very different knowledge bases, and you have to be able to communicate and work and break out what the tasks of a project really are to keep it moving smoothly. And then you also have to be able to work independently. I've always heard it said that going to college for civil engineering, you don't learn everything that you're going to be doing on the job, but you learn how to be an engineer and how to learn engineering. And that's what so much of those first couple of years of being in your field in engineering is working with mentors and independently to solve your problems and gain a greater knowledge base of your discipline and your field. Oh, I'm sorry. There we go. So specifically structural engineering. This is the design of buildings, bridges, tunnels, dams, retaining walls, even pipes sometimes. And that means you have to understand something very basic to our field, which is the loads that we have to design for. So you will have things like dead load, which is a self weight. As you all know, if you've competed in Candy Bridge before, Candy is sadly not weightless and it has to be able to stand under its own weight. Then you'll have things like live load, which is the pedestrians and the vehicles and the train loading that we put on there. Or on buildings, rooftops carry a lot of snow, or if you're in a place prone to earthquakes, you design for seismic load. And then those tall skyscrapers, they have massive facades that are going to capture a lot of wind. And then impact, which is like when you walk about, you're amplifying the load when you're pressing your feet against the ground, or every time a wheel on a train turns, it's going to be inducing an amplification of that live load. And then the most important thing is kind of, as you can see in that diagram below, which is your load path, which is how is this load going to get through my structure to my supports? In your guys' case, it's going to be how is it going to get from wherever that load is being applied at the center of your Candy Bridge to get all the way to the bases on the side. And that's going to be the most important part of your design, which is how are you going to take that load and what is it actually doing to your structure, which Thomas will be talking a ton about. So next is kind of what does actual bridge design look like? You're going to be dealing with project layout and coordination, then actual design. And after your design, you're going to be doing maintenance on your projects, which sometimes requires design, like designing repairs. Project layout and coordination is working with your multidisciplinary teams to put together what do we actually need for this project? What does this site need? Does it need new bridges? Does it need new stormwater or sanitary sewers? Is it going to need soil slope stabilization from your geotechs? It's coordinating with all of these different disciplines to dissect what you're looking at in your project and figuring out what are the needs of it, and then breaking that into what your design tasks actually are going to be. And then you move to design, where you have your geotechs create, your grading slopes. You have your H&H figure out where you need to be draining water and where it needs to be flowing on your job site. You have your structural engineers designing our structures for whatever the capacity is required by our traffic engineers and telling us what kind of traffic are we actually going to be seeing on our structure. And then after it's been designed, we try and keep these structures and these job sites alive for as many years as possible. In railroad engineering specifically, some of the structures that I get to design repairs for are from the 1914s. We are maintaining very old infrastructure in some cases because we've had a lot of amazing people doing maintenance on our projects. And then just kind of a small, simple little overview of the types of bridges that have been designed throughout the years. So as you can see, this is a beautiful stone arch. This is one of the original structures that was designed. You know, this is the Roman aqueducts and what they were based on. It has been one of the stronger shapes within human history and one of the favorite buildings for bridges. Next. And then you'll have a beam, which in this case is what's called a box girder beam for concrete. But these are basically slabs of a material or an eye-shaped girder that is used to support weight. Then we have some of the more spectacular ones like suspension, aka the Golden Gate Bridge, is one of the most famous suspension bridges in the world. You know, they have those center piers, then they'll have a really long, strong tension cable with lots of different cables coming off of it to hold up the deck of the bridge. And then we have cable stay, which is a little bit similar, but instead of having those long, strong cables that other cables hang off of, they go directly from the piers to the bridge decks. Very beautiful, very architectural. And then we have a classic simple truss, which steel trusses are still all throughout the United States. They are one of the most famous architecture and infrastructural elements of railroads and some, well, I guess not anymore, roadway bridges. So I hope you guys enjoyed this little segment on what it's like to be a structural engineer and getting this taste of some of the basic things that you might get the chance to design if you work in railroad.
Awesome. All right, it's my turn. Thank you, Joe. So what Joe did was he gave a really great overview of load path. And so load path, as he mentioned, is when we apply a load to a structure, how do we get that force to our supports? You know, everything eventually needs to resolve into the ground. And in our case, that load rig that you've seen pictures of, that is our ground or our reaction frame. So we need to get our force from the piston out into the sides. And so when we are moving force through a structure, we create internal forces or internal loads on what we call members. Members are pieces and chunks of our bridge that have to handle these forces and move them from the application point to the supports. So there are 4 relevant loads that we're going to talk about today. There's some additional, but we're not going to focus on those. We're going to talk about compression, which is in the upper right-hand corner, trying to squish a member. Then we have tension, trying to stretch a member and elongate it. Bending is over in the bottom right, and that's, you know, trying to, just like you imagine bending something, you create some tension and compression forces when you do that. We'll go over that. And then shear is kind of trying to like tear or rip something apart by pushing on it in 2 opposite directions. So those are the 4 main: compression, tension, bending, and shear. And we'll go into those each here. So compression forces, if you see the Coke can up in the upper right-hand corner, that's what crushing would look like. That's, you know, you stomp on a can and that's putting a compressive force into that soda can and you crunch it down, and that's a failure. You know, we failed that Coke can. Buckling is a little bit different. It'd be if you imagine stacking 2, 3, 4, 5 Coke cans on top of each other and trying to press on them. You probably won't get that nice squish shown in the image there. It'll likely want to pop out and just kind of fall apart. So that's buckling. So those are the 2 main, what we call failure modes that can happen in an element or member that's taking a compressive force. So kind of mixing some things in here, some high compressive strength materials. So when we're talking in construction, rock is really great in compression and not good in tension. We'll go over that. Concrete is great in compression as well, and so is steel. And then if you bake it just right, gingerbread is actually really good in compression. Some of the forces that we're able to get in our bridges are surprisingly high. So we got a little image showing that concrete is just like gingerbread. And then next slide. Perfect. So gingerbread with high compression strength. How do we do that? How do we make that? We want something that's really dense and really hard. So maybe not your favorite gingerbread to go and eat, but we're going for structural integrity here. So we want something that's pretty condensed and pretty thick. And then we're going to talk about this larger section area. That also helps in compression. We want something that, say we have the same amount of gingerbread, A and B, or our left hand and our right hand. We can make the shape larger and leave a void in the middle. That's going to handle compression better than a more condensed, smaller piece of gingerbread, if that makes sense. So we call that section area. And if we really want to get into it, moment of inertia is what we call that in structural engineering. Don't worry about that till college. But that's what that is doing. Expanding your area helps to avoid buckling. So a little quiz question. I'll make it rhetorical. We don't have to answer this one, but out of A and B down there for compression loads, which gingerbread is going to be better? I think we probably would all come to the answer that B there is the better gingerbread for compression. It's dense, it's thick. If you try to bite into it, it's going to have a nice crunch. Whereas the one on the left is kind of like cake. There's some products in there that make it fluffier and lighter. That's not going to perform as well in a structural application. Okay, so now some tips and tricks. Take these with a grain of salt because these are just things that I have found over the years. I've only done the competition twice, but I think I came across some good tips here. So my first tip is that this is like a science experiment. You should experiment and record and kind of come up with some test recipes. That's like half the fun of it, truly. So what you can see down on those two images is, what I created as test panels. And they are, my recipe number one, which I'll go into, but I recorded the initial dimensions of it. And also I stabbed it a bunch with a toothpick. I wanted to see how that baked, if it got rid of the gooey center and made it stiffer throughout. And then after that, I recorded how long I baked it for. I flipped it once and recorded how long I let it sit on one side versus the other. And then I recorded the final dimensions of it. It happened to shrink in this case, which you can kind of see in that lower right sticky note. So have fun with it, experiment, and record what you're doing so that you can come back later and have something for next year's bridge and the years after that. I would strongly advise avoiding softening additions. I'm no master baker here, so the only one I could come up with was corn syrup. But I know corn syrup is what makes gingerbread sweeter and softer. And to be honest, we're going for edible here, not delicious. So we want to be able to choke that down, but we don't need it to be great and tasty. Okay, so we want the best structural gingerbread that we can get. And so, yeah, avoid things like corn syrup or, fluffing agents, things like that. And then think outside the box. So we don't necessarily need to make it quote unquote gingerbread. My hint here is to check out the recipe for a hardtack cracker. These hardtack crackers, I think, came out of the Great Depression era, but they're thick, they're really strong, and they're really simple ingredients. And so, you could add a little ginger, add a little sugar to make it quote unquote gingerbread. But just think outside the box. Do what you can to make your strongest members for your bridge. And then finally, just brainstorm ways to create uniform shapes. So you'll be best off if you can duplicate and replicate a shape that can be, repeated throughout your bridge. We have maximum panel sizes, which Cameron might touch on later. But you can't just bake one giant conglomerate gingerbread bridge. You need to construct it out of smaller pieces. So if you can do that by creating uniform panels that have a similar thickness, similar edge dimensions, that should help you out a lot. So you can see in the image on the right, you can kind of see it curled on the edges. So my goal is to try to get rid of that. Maybe you set a pan on top of your gingerbread as you bake it so that it kind of keeps it nice and flat. Just brainstorm ways to try to make those panels as uniform as possible. All right, so that was all compression loading. Now we're going to talk about tension loading. Tension, like seen in the upper right-hand image, is like trying to stretch a rubber band. So when we're putting tension into our members, we're trying to stretch it or elongate it, or we're going to rupture or tear it. So a rubber band stretches until it can't stretch anymore, and then it breaks and snaps, right? So that's the forces we're trying to handle when we're talking about tension. In construction, there are some really high tensile strength materials. Steel is one, rope. Rope is a really good one to think about because if you think about a standard rope, it works really well when you're pulling on it, but it doesn't handle any compression. You try to push it and it just is like a noodle, right? So there are members that work really well in tension, but not in compression. As far as bridges go, candy is going to be a good tension element or tension member. And then gingerbread, despite it being good in compression, it also can be used as some tension members as well. So, in the lower image, like a steel braided wire rope, like Joe showed on a lot of those bridges, those are absolutely fantastic in tension, but they're so skinny and so floppy that they don't work well in compression at all. So we need to keep that in mind when we're picking out what elements we're using. We need to be cognizant of what forces are in those members. And we'll go into that a little bit as well. But that lower right-hand image is taffy. If you imagine taffy is really good in tension, I would say it's kind of strong. And yeah, that's all I got for taffy. All right, shear loading. So shear is the force that makes things want to kind of slip and tear apart. So that's why when we talk about scissors, I think it's an older term, but people call them, kitchen shears. They're shearing or they're ripping things. So that image in the upper right-hand corner is, tearing a piece of paper by putting shear into it. Going straight into the materials that we like to use for shear strength in construction. Again, steel, concrete. I feel like I have a theme here. I must really love steel and concrete, but those are some good high strength shear materials. And then again, gingerbread. Gingerbread is strong. It acts really similar to concrete, especially if you can reinforce it with some additional tension elements. Hint, hint. So similar rules to the high compressive strength gingerbread. We want something that's dense, really compact and strong. We use the term brittle sometimes. Brittle is something that kind of takes load and then all of a sudden snaps and breaks. That's kind of what we're going for when we talk about our gingerbread here. And I would say again, the stiffer, the more brittle gingerbread is going to perform better in shear than say a nice gooey piece of cake like gingerbread. But an important piece to understand here is that, we talked about these different size panels. We need to glue these all together or stitch them together to make a continuous member or continuous bridge. We need to bind those together somehow. And that binding agent or that glue is what is going to help us resist a lot of those shear forces. We need to make our members act together. So my recommendation here is sugar. It's as simple as that, just dumping a bag of sugar into a pot on the stovetop and stirring it continuously. That's how you make caramel. And so there's nothing else really needed. You can obviously experiment and add things to make it more tacky, make it softer. But as simple as that, just white granulated sugar in a pan with heat and stirring makes this hot molten lava goo. You want to be really careful with it. It's extremely sticky. It's very, you don't want to get on your hands. But if you pour that over your members or use that as glue to stick them together, it dries into a really stiff caramel and it works pretty well. Okay, I believe this is our last failure mode, loading case, but this is called bending. Bending is, you take a ruler and you just try to bend it like that, right? The unique thing about bending is that internally you have compression and tension, which we talked about earlier. You have them both acting at the same time. So for the purposes of our bridge, what we call a simple span bridge, a good rule of thumb is that we're going to have compression in the top of that bridge and tension in the bottom. So think we want good compression elements towards the top, good tension elements towards the bottom. And so what I always like to think of is a smiley face. The bottom of the smile is your tension. You're wanting to open up the bottom end, which is pulling apart. And then the top side of the smiley face is trying to crunch it all together. So that's where we get our compression. Okay. Joe actually showed this type of bridge. I think it was maybe one of his last bridges shown. He had that very nice looking steel truss bridge. So we're going to go a little deeper into structural mechanics here. If you would imagine, pretend you don't have a truss bridge, and what's shown in that image was just a solid chunk of steel, just a big, deep member. You have something that would be really heavy and really inefficient, but it would do the job, right? So what structural engineering has done, and what we get to practice every day, is making things efficient. And so you can picture that we took a big, thick steel beam, and we actually cut out those triangles in it to only use what was needed. And that's where this whole strength to weight ratio comes in. It's more efficient, and we get rid of a lot of the extra weight that was maybe once there on a bridge. So by picturing this as one big, deep beam and removing chunks or areas of steel, we can see that we're improving our strength to weight ratio, and we're using what we call these members, these vertical, horizontal, and diagonal members in ways that they perform best. So you can see again in this bridge example, we have compression in those top members, tension in those bottom members. And those diagonal members were actually a really efficient way of handling shear. And we take that shear and we put that into tension or compression through those diagonal members. So structural engineering is all about really improving and value engineering things to be the most efficient. So we all love the bridges that take the most load and have some crazy explosion at the end. But really the goal of this competition is efficiency, strength to weight ratio. So if you say your bridge only takes 20 pounds, but it was really light, that could perform better than a bridge that takes 200 or 300 pounds. So just keep that in mind as efficient members that are working well together. And then this is just the most spot on example that I could find. I was looking back through some old photos. So if you do want to go look for inspiration, the Gingerbread Bridge Competition website has a gallery from past years, and it's really helpful to go look at old bridges. This is one from JVA. We love JVA. They always do a really great job with their bridges. But I really love this one because they drew on their bridge showing the forces. So if you look closely, the upper right-hand member says compression, and it shows those arrows going, putting that gingerbread into compression down into that lower buttress element. And then you can see that bottom member, it's kind of obstructed there, but near the arrow, you can see in red font, it says tension. And that's exactly what's happening. The bottom of that bridge is in tension, the top is in compression. And you can see that they actually added some cool looking like bolts or rivets, or maybe dowels, some candy elements to that bottom member, because we're trying to connect those and keep that tension force flowing throughout that whole member. So really cool example here. A lot of the bridges that we do see perform well have some sort of arch incorporated or some sort of triangle. But one important thing to note about the rules, and Cameron might go into this, is that the bridge needs to be more or less self-contained. It can't push against the load rig. So if we were to remove that bottom tension member, you can picture that this thing would just want to splay out. So we need something down there that is resolving the tension force because we can't push up against the load or the reaction frame. So that concludes my section of it. Yeah.
Perfect. That was awesome. Thank you, Tom. And yeah, as he mentioned, I'm going to go in a little bit into the rules, just a couple common questions. But I do want to just reiterate that the rules are posted on that same website where you can find the photo gallery. So I have a link here, but it's just gingerbreadbridge.com. And there'll be a link to the Denver competition versus the Portland one. And on there, there's rules, photos, past winners, sponsor information. So a lot of great information on the competition is at that website. But a couple just general rules that I've gotten a lot of questions about. One is building materials. So your structure does need to consist exclusively of some type of gingerbread or graham cracker panels, and then edible candy for tension cables, connectors, that sort of thing. And then as Tom mentioned, you can use sugar, icing, those sort of things as your glue, but it does need to be candy and it does need to be edible. In addition, all display components need to be edible. So as you've maybe seen in some of the photos for that architectural design, you're allowed to bring a design board and then also decorate around your bridge with different architectural elements for that part of the competition. Those also need to be edible. And those can be scraped off before you load test so that you can reduce that weight. But again, needs to be edible materials. Geometry constraints. Tom touched on this a little bit as well. The bridge span needs to be a minimum of 24 inches, and that's so that it fits on the load rig, which I'll show some photos of here in a second. But we do recommend about 30 inches. That way you have plenty of bearing on either side of the load rig. That 24 just kind of barely gets you there, and sometimes can be, you don't have as much area to bear on the load rig. So we do recommend 30 inches. I think the maximum is maybe 32 or 33, but you can't do too long. Otherwise you hit on the sides of the load rig and could, again, like Joe was saying, or Tom was saying, you can't push it against the sides. So I'll show some images to help clarify that in a second. Bridges need to be 12 inches tall, and they also need to be 6 inches or less in width. So those are the height and width requirements. And then as Tom touched on, those panel dimensions, the maximum panel size is 8 by 4 by 3/4 inch thick. They can be oriented in any direction, but just need to have those smaller elements for your panels. And then the maximum size for that display board that I talked about a second ago is 36 by 30. And there's all of this is in the rules at that link. There's some other helpful images there as well if you have questions. We'll also open it up for questions here soon. So here's that test rig we've been talking about. So as you can see here, right to the edge of the supports is that 2-foot dimension. So if your bridge is exactly 24 inches, you're going to have a tough time actually bearing on the sides of that support. So that's where we recommend about 30. In total, we have another 5 inches here for these landings. So that's where I think the range is 30 to 33. But if you get too long, then you start pushing into the sides, those 5-inch side panels that you can see there. So that's what you have to be careful of. Is if your bridge starts to push against the sides, we'll have to stop the test and your weight will be the amount before it started pushing into the sides of the support. So this bridge on the bottom left corner might have an issue, like Tom was saying, since you don't have that tension element connecting it, where it might start splaying out and putting the load into the sides, which would stop the load testing for your bridge. So important to have that tension element there and make sure you hit the dimensions. 1 foot max is the height. We do have some different things if it's shorter to help put in some blocks or things to get you to that height. So it can be a little bit shorter if you'd like. We have some blocking. We have some sugar bags to hoist it up, different things like that. But that is the load rig. I guess, Tom, do you have anything to add on the load rig?
No, I would just take advantage of that bearing area, like you're saying. The more bearing you get, you do better for that crushing failure that we talked about. So I would try to maximize that, definitely. But no, that's all great stuff.
Perfect, thank you. Okay, and then I do want to get into our sponsors really quick and thank all of them this year. We have a lot of great sponsors. Our platinum this year are DeWalt and the Colorado School of Mines. So big shout out to them for being our 2 platinum sponsors. Gold, we have Kaufman, JVA, Simpson Strong Tie, Vimcore, WJE, Wallace Design, SA Miro, Lamwood, Keller, Benish, KLNA, and Kiewit. And then for our gold or silver sponsors, we have Dursa Hendrick, BNSF, Anchor Engineering, and Nucor. So you'll hopefully be seeing those guys around at the competition. A lot of them are planning to bring some booths, and then some of them will also be designing bridges this year, which will be awesome. And speaking of them, we are doing a professional mentor program this year with engineers from our sponsoring firms. So we will be assigning those to interested student groups. If you're interested in having a mentor assigned to your school or your team, please send me an email at that ymg@seacolorado.org, and we'll link you up with a mentor. In that email, let me know if you're looking for in-person or virtual support from your mentor. That way I can make sure to set you up with someone that can has the time and is wanting to do that. So again, these are some really great photos from last year's competition. The Gouda Bridge has some really great architectural elements. They have a little candy mice and a little fun back display board. So this was one that won an architectural award last year. And then here's a team from the Colorado School of Mines. They made theirs look like a dragon. And you can see here they used more graham cracker and icing. I think this one was maybe sugar for their combining element, but yeah, two really great examples. I think that is all that we have planned. We wanted to leave enough time to do some Q&A. So with that, I think we'll conclude the presentation and open it up for questions.
Hi, this is Catherine Barnes. Can you hear me?
Yep.
I can.
Okay, so I've got, I run engineering clubs at Centaurus, and we've got three, possibly four groups that want to join. Is that too many for mentors? Because I've got some mentors here I can set them up with. I just didn't want to overwhelm your team.
Yeah, I think so far what I have signed up would probably be doing more one per school at this point. I'm hoping to
Okay.
find a few more, but my goal right now is at least one per interested school
Okay.
for all of your teams. And then if I find a few more, I can let you know.
Okay, no, that's great because we've got a parent who is a civil engineer, structural engineer, so he's going to mentor the teams also.
Oh,
So,
fabulous.
we've got that. So thank you very much.
Yeah, of
They're
course.
so looking forward to it. They're already talking about how to make their gingerbread.
Oh, good. I love that. That's fantastic. Guess if there aren't any more questions. Oh yeah.
Yes, with schools and like multiple groups, do you have any tips on baking the gingerbread just for consistency, like with a team? Is it better to have like one person in charge of gingerbread, like one person in charge of the design? Like, what have you seen that works best working in teams and getting all the parts together?
Yeah, so I can speak to that. I know JVA, who's consistently performed really well. They do designate certain people in their team to just be bakers, just be architectural people, just be constructors. So I think keeping baking to, if you sent each person home to bake their own panel and came back together, you'd get wildly different results. So I think keeping just a couple bakers, and obviously school teams, everybody wants to construct it. So I think you should have as many students construct together as possible. But for the baking, I would just try to do it in bulk and have just a few assigned to that piece.
And I saw one other question in the chat about knowing if we received an entry. I'll plan on sending an email out hopefully today, to everyone that's currently registered. So maybe let them know to check their emails, and if they don't receive it, I might not have received their registration. So I'll get that sent out today or tomorrow, and that way you guys can have that as a confirmation that you've registered. And on that note too, if I'll send those emails and send them to all the instructors as well. So I'll probably ask in that email for your quantity of teams and that sort of information too, just to make sure we're all on the same page. Registered team so far, I haven't looked in a few days. I know we have four to five teams from CU registered. We have 3 different homeschooling groups, some folks from Centaurus. We have quite a few. I haven't done a count recently, but I can put that information in the email that I send out to the student teams and their instructors. But yeah, we're happy to support as many teams as want to register. We believe we should have $75 for all teams for expenses. If you have more, keep your receipts and submit those. And at the end, if we have some budget to help cover anything additional over $75 per team, we'll try to do that so that it's a low cost for you guys.
I'd love to see that there's several Minds teams. Awesome, Hongyeon. It's exciting.
Yeah, we'll have some more competition with CU this year, so we'll have a little bit more of a college battle.
Nice.
Yeah, great. I'm trying to advertise this for all of my classes right now. So hopefully, I think at least I know 2 teams already trying to register right now. I will try to encourage more later.
That sounds great. Thank you so much.
Uh-huh.
Guess we'll wait a little bit longer, but unless we don't have any others, I did also want to mention at the competition, we will be having some fun door prizes again. So that'll be something fun to look forward to from our sponsors as well. So we'll try to kind of keep it moving. I know last year too, we did some tours. So if you're interested in setting up a campus tour at the School of Mines, I'll send that in my email as well, but let me know and we can coordinate with some of their folks there to give your students tours of campus, which could be a fun way to kind of extend your field trip and see the college campus. Awesome. Yeah, thanks, Catherine. We're happy to put this together and post it as a resource for everybody. All right. I think we'll wrap up, but thank you guys all for joining, and I'll get this posted on the YouTube shortly for reference. But thanks all and have a great rest of your day.
Thank you.
Thanks, everyone.
Thank you.